So everybody got a nap in during the last session, so you're going to be wide awake for this, right? Okay, they didn't have cookies or anything out there, did they? They did? We're in trouble because we're going deep here. I love giving technical talks. You guys probably saw me at the keynote. That's not my typical talk that I give. I like to go deep. So if you guys want to go deeper into any particular elements of this, just let me know as we go. We're going to get to things like using spreadsheets for big data. You're going to like that, all right? But really what we're talking about is modeling and simulation for Accumulo applications. So trying to figure out how to get your application to reliably perform well at scale. So there are a bunch of different things that you would want to optimize in an application. In many cases, you don't know what those things are until you've run the thing at scale, right? And maybe that's too late. Maybe you want to be able to get ahead of things. So if you're trying to really discover factors that you didn't really expect but are actually going to become important at scale, you can use some of these techniques for that. And really it comes down to reducing the risk when you're extrapolating, right? So if I run tests on a 5-node cluster, but I want to scale up to a 5,000 node cluster, there's some risk of extrapolating over 3 orders of magnitude, right? Maybe I got the scalability numbers wrong. So how do you really get a handle on that? And how do you detect that ahead of time without buying a 5,000 node cluster? Does anybody have a 5,000 node cluster that I can borrow? No, okay. I don't have one either, but some of my customers do. Okay, so we're going to talk about micro benchmarking. We're going to talk about analog simulation, so pretending we're running the thing but not actually running it. And then predictive model validation, so looking at a very tight accounting for everything that's going on and try to detect any kind of deviations in accounting at smaller scale so we can be a lot more confident in our extrapolations. All of these things get used together, and I'm going to go into each of them and talk about how you code up the technique, what kinds of insight you can get from it, and how you sort of use that in a cycle to improve your code. So hopefully by the end of the talk, you guys are all going to be able to do this, take it home, code your own simulators, and so on and so forth. We're going to start out with micro benchmarking. So the goal of micro benchmarking is to optimize the crap out of operations that happen in tight loops. So we also want to really isolate different components that can have unexpected effects, right? So maybe one component in your JVM is using a lot of memory. Another is slowing down because it's doing object allocations and has to compete with it. But you didn't necessarily expect those things to be related because it's in a subsystem. With micro benchmarking, we're going to forget all of those complex interactions and leave that to things like simulation and predictive model validation. All right, so I'm going to use as an example an R file sorting output format. This is part of the ingest pipeline that we use inside of Sqrrl, where we take data in, and in a map job, a map-only job, not map-reduce, but just map, we take that data, we split it up into splits. For each split, we read it one record at a time. We map it into a series of key-value pairs that are associated with indexes. Did anybody see Aaron Cordova's talk last? Anyway, you probably saw some of our design patterns slightly represented in his talk. So our mapper generates a bunch of key-value pairs, but it's essentially generating them in random order. And to get data into Accumulo, if we're going to bulk load it, we need to get it in sorted order. So we buffer it up, we sort it, and then we write it to a big R file. That lets us get pretty significant ingest rates as long as we do our partitioning properly, which just so happens we do. But I'm not going to talk about that during this talk. In this talk, I'm going to talk about places where we can really micro-benchmark to figure out techniques for optimizing these very specific parts of the code. And these are things that are essentially tight loops, right? So I've got a mapper here, and inside of my mapper, I'm going to take one document, process a bunch of key-value pairs out of it, right? And just do that over and over again, right? Spending, a microsecond per document, something like that. further downstream, after I'm collecting these key value pairs and sorting them, I've got a sort operation that's essentially a tight loop operation. I have to compare keys, maybe swap them, do some number of those operations in a tight loop. And there are other related things like the structures that I use for that. So it's not necessarily in a tight loop, but it's handling the output of something that's in a tight loop. So the in-memory buffer that we're using in this case fits that general category. All right, so with micro-benchmarking, we're going to see what we can do to really do the best job we can at these small things before we take it to an overall system. So to do a micro-benchmark, you basically write a program that looks like this, right? You measure the start time, do many iterations over something, measure the end time, print it out, right? This is like the simplest micro-benchmark that you can write. And there's not much to it. This is basically almost compilable code here. So we benchmark it, we compare. So we're not just going to benchmark one thing. We're going to do A/B testing. We're going to test out different techniques here. Synthesize our knowledge, rewrite the thing that we're doing to use a different technique, and repeat. So benchmark again, compare with previous results. And the point of micro-benchmarking is really to get this into a tight loop. Not just benchmarking something in a tight loop, but tight looping around the benchmarking process itself. So the more iterations I can do with modifying the thing and rerunning it and getting the results and analyzing them and so on and so forth, the more I can optimize my code. I'm not going to get it right the first time, even though I'm a super genius and know everything about computer science. There are going to be things that surprise me and any of you guys in the room as well. So there are tools you can use to do this. We use Java micro-benchmarking harness, sometimes JMH. It's pretty neat. But it's not a lot more complicated than just this basic loop. Now, if you want to get a little bit more insight into what things in that tight loop are taking a lot of time, then you can use things like a sampling profiler. So a lot of science around how to do that, like figuring out at what points it's actually sampling, if those are evenly distributed and all that. But for the most part, something like JVisual VM with a sampling profile is going to give you a pretty good first-level insight into what's going on. Enough that you can rewrite your code and remeasure it. OK, so when we do this in our example of our ingest pipeline, we get all sorts of insights, right? So things like serialization and deserialization of keys can become quite significant. So if I have to, when I'm doing my sort operations, if I have to deserialize my key into just an accumulo key, rather than keeping it in a binary serialized form of it, that's going to start to dominate, right? I'm not going to be able to do as many comparisons as quickly, and maybe an order of magnitude difference. So holding on to objects, Java doesn't like that, right? Small objects used for a very small period of time, Java's great with dealing with those. Holding on to objects over seconds is expensive, and the memory manager starts to become a lot less efficient. Sort boils down to compare and swap, rather. So if you're minimizing the number of bytes that you compare, your compare can be faster, and therefore your sort can be faster. So this gets into like the data structure that we use. If you can get to the part of the key that is going to be different. In our case, the column qualifier rather than the row and the column family. If you can just compare those things, then you're going to be able to do your sort a lot faster. And then minimizing the cost of swapping by maybe introducing indirection to store pointers to the keys, so you don't have to worry about size of allocation or anything like that. There are a lot of techniques that are kind of well-known in computer science. You can start applying them here, and you really see through the micro-benchmarking that they make a huge difference in performance. Along this process, you also end up putting in things that you think might make a big difference and end up doing worse. Like we tried to use merge sort instead of quick sort here. And it boils down to, with quick sort, you get a better cache hit rate inside of the processor cache. So you guys did eat a lot of cookies, didn't you? This is supposed to be like, yeah, cache hit rate and processor. OK. Anyway, so we found quicksort was actually faster, even though merge sort has a theoretical better bound on performance. All right, so once you've gained these insights, then you code up your little function with the best known algorithms, whatever you've determined is the best through your micro-benchmarking, and you measure again. So for us, we got into things like, this was the data structure that we used for buffering data coming out of the mapper before it got sorted. So we're doing things like abstraction between the row and the column family and the encoded column qualifier. Right? And we've got the column qualifier and visibility encoded in a way that is comparable without deserializing it. Right? Tons of techniques you'll learn as you start experimenting with this. And the more loops you can do, the more good techniques and the better performance you can get in this type of application. So we ended up with basically on a single node, we can generate, sort, and write 7 million key value pairs per second. So that's pretty good performance. Nobody else is getting this kind of ingest performance into Accumulo. So we're pretty happy with it. But micro-benchmarking, we're still focused on the micro aspect here. And if I'm talking about scaling up my processing beyond just what we can do at that small scale, there's still a lot of unanswered questions. What if I'm running something else concurrently and it's got some kind of unexpected interference? Or do my algorithms have a point at which they start to do an inflated amount of work for some reason? So for that, we're going to get into technique number 2 here, analog simulation. So with analog simulation, we're really trying to test bigger than we can afford to test. So maybe on a 5-node cluster, I'm going to simulate what I can do on a 5,000-node cluster. And moreover, I'm going to simulate what I can do in a year on a 5,000-node cluster in a couple of seconds on a 5-node cluster, or possibly even on my laptop. So in Accumulo, we're going to get into some of the details here of what goes on as we do maintenance for data in Accumulo. But there's this compaction thing. Anybody know what a compaction is? Anybody have a lot of cookies for snack time? OK. Compactions happen in the background. When you think about how much work a database has to do, you can boil that down to things like a write amplification factor. I'm going to talk about exactly what that is. But if I write a key value pair and I have to touch that thing 5 more times, now I'm doing 5 times as much work as I initially did to ingest it. And a lot of times in Accumulo, that's hidden, right? Like you don't see the compactions. And when you measure your ingest the first time, the compactions haven't happened yet. They happen behind the scenes. And they start to build up over time because I have more work that I have to do to sort the data that I just ingested with all the data I ingested over the last year, or however long my partitions last. So in Sqrrl, one of the things we were looking at was a partitioning strategy and its effects on this write amplification factor. We didn't have years and thousands of nodes to test it, so we wanted to simulate that and get a pretty good idea of what was going on. So let me give you a little background. If you saw Aaron's talk, you saw something like this, which is a document distributed index table design. Basically, we take a single document, we ingest that document and all of its index entries into a single partition, and then a query comes and it queries all of the relevant partitions. Now with Sqrrl, all of our data is basically time-oriented, right? We deal with cybersecurity threat data, so the more recent data tends to be of higher value, and people tend to query for things in windows, time windows around events, not Windows operating system. Yeah. So the partitioning strategy that we pick here, if it's aligned to the query, It basically means that we're going to say, all right, a certain time range of data is going to correspond to a certain set of partitions. And that allows us to do a lot of things like the partitions only grow for a certain time period, and then they're full, and we don't have to worry about compactions because they're already optimized. Other stuff on the query side, I'm not going to go into the query side of this because it's less important for the simulator I'm going to talk about here. But the Accumulo compaction algorithm basically works like this. So if we take a set of files that are associated with a tablet, those files are going to have different sizes. Right? So maybe I've compacted a bunch of data together a month ago and created this gigabyte-sized file, but I just ingested a 1 megabyte-sized file. And since then, I've got this distribution of file sizes associated with a tablet. The algorithm that Accumulo uses for deciding what files to compact together lets us trade off between very aggressive compaction, which might recopy all of our data every time we ingest anything, and a very lazy strategy, which would say never compact anything together, and just at query time, just merge everything together. So one side is more efficient for ingest. This side, actually. This side is more efficient for query, right? Because you only have to query one spot. So the algorithm inside of Accumulo works like this. I take the files. I take a subset of the files. I compare the total size of those files to the largest one. And that gives me a ratio. Has anybody ever heard of a compaction ratio? So the compaction ratio is our threshold that we compare against the ratio of aggregate files to a single file. And basically what we do is we take the maximal set that has a ratio bigger than that configured ratio and compact those together. So in this case, if 3.24 is bigger than our configured 3.0, we get a check mark and we kick off a compaction. So what that looks like over time is basically we've got a tree forming of files coming in, getting compacted together, more files coming in, getting compacted together. Eventually, you end up with a smaller set of files here. All right, you want me to do the animation again so you can get more pictures along the way? I worked hard on this. OK, so you see the grayed out files. All of the data in those files has been recopied to something further up the tree here. And every time I take a key value pair and I write it to a small file, if it gets compacted and then compacted again, there's a write amplification factor of 3 for that key value pair. Right, so I've written that thing and read it 3 times. And if I'm really, really trying to optimize my ingest performance, I really care about this factor. OK, so what we want to do is we want to scale this up, pick some different partitioning strategies, and see what the effect is on that overall write amplification factor. So I'm going to build a simulator. And my simulator is essentially structured like this. At the top in the cylinder, I've got a priority queue of events. Right? And this priority queue is going to prioritize things in time order. So the first event with the smallest time comes out of the priority queue first. An event basically is this simple interface which has an event time and allows me to process it. Right? And with that, I'm going to have my main loop here, which apparently doesn't fit in this box. It did when I created the slide. Anyway, the main loop says, while you've got some stuff in the queue, pop the first thing out of the queue, process it, and that's it. Right? And now, what does it mean to process the event? Well, inside of the process function there, we're going to do things like modify the state of the simulator. So I'm going to keep some other classes around that have to do with that state. But that could be anything. The simulator doesn't really care. And then typically, the event itself will generate more events. Right? So if I ingest data, that's going to generate an event to check to see whether I need to compact the data. So when we take this and we try to use this simulator design for compaction simulation, we get a little more specific. So we're going to simulate the ingest of data, and we're going to simulate the triggered compactions that happen downstream of that. We'll have events that are associated with the bulk load of new files, events for the start of a compaction, events for the end of a compaction. And as we create these events, we're going to measure state associated with how many files are associated with a tablet, right? And maybe measure that over time, get some averages. We're going to measure the total input, the total bytes that we end up compacting. And as I said, we're really trying to explore design decisions around compaction, partitioning. Not compaction, compaction related to partitioning choices that we make. We also, at the same time, we're going to look at things like if we modify the compaction ratio and change it from 3 to 4, what's the effect of that? I mean, it's probably obvious to you guys what 3 to 4 does in the system, right? No? OK. Well, I'll tell you a story. Originally, when we put the compaction ratio in there, we had a default of 1.3, which seems perfectly reasonable, right? 1.3. How do you pick a good compaction ratio? At the time, we had done some kind of basic stuff to on paper, say, all right, if we kind of go through this, 1.3 kind of sounds reasonable. So if I've ingested 3 megabytes of new stuff and I had 10 megabytes, I'll compact those things together. But that actually ends up with a very high write amplification factor. So at some point, we changed the default to 3, which ends up with a very low write amplification factor. And it's nice to be able to look at this from an application perspective as well, because every application will have a slightly different impact on the amount of work you're doing based on these settings inside of Accumulo. OK, so when we run this type of simulator, we get something that looks like this. On the left-hand side, I've got, sorry, on the right-hand side, your right-hand side, input parameters. So things are like, I can set a compaction ratio. I can set how many bytes per second I can process through compaction. 2.5 megabytes a second is basically what we get when using things like gzip. I had some special things about limiting what the max compacted file size could be. This one is not particularly limited, as you can see by that large number. But anyway, I'm not going to go through all of these. With a given set of inputs, we can very quickly evaluate weeks or months or even years of running a system and ingesting data into a set of tablets. And within a couple of seconds, we get this output that says things like our write amplification factor, in this case, was 5.38, which is, it turns out that's pretty good. Right? Not a lot of databases get write amplification factors that low. But as we explore different sizes of time sizes of partitions and different factors in here, we can really hone in on balancing things like write performance and read performance. This other factor that I have here, average files over time, 8 files on average. If I have to merge those together for a read, that's pretty good. Right? It's not, it's not one file, but it's also not dozens of files, which would slow down my latency of bringing the first record back. So there's always a trade-off here. But simulators really help us get a lot of insights into that. All right, so what did we figure out here? We figured out through this simulator that we can do things like change the compression codec between small files and large files. If I'm only going to output a megabyte, maybe I'll use Snappy. But if I'm going to output a gigabyte, I'm going to use gzip, right? Because that means I'm not going to recompact that large file as frequently, right? It's basically been compacted, and it's unlikely to compact again as long as my tablet doesn't keep growing. A limit on the maximum file size for compaction has a huge impact on kind of the stability of the write amplification factor. All right. These are things that are really hard to pick out if you're just observing a running cluster, because there are a lot of different things that could happen on that. The simulator helps us explore a lot of different paths here. So we've also used simulators recently for optimizing the query read-ahead thread pool. So inside of Accumulo, there's this thread pool. When you do a query, it basically breaks it up into chunks and schedules it in this thread pool. But if I'm running a long-running query at the same time as a quick query, my quick query has to wait for some number of iterations of long-running query. So there are better things that we can do there. We've been exploring all sorts of things like that, right? Dealing with secondary compactions and all that kind of stuff. And the simulator has been invaluable for it. OK. All right, so we've looked at micro-benchmarking so far. We've looked at simulator. The simulator isn't running my real code. My micro-benchmarking isn't running enough of my code to get a full picture on it. So how do I really bring all these things together and make sure that my overall system is going to perform well? That's where this third technique comes in. So predictive model validation. Woo! Right? OK. So when I'm creating a predictive model, that means I'm going to say, based on the things that I know about how this thing should run, it's going to do these activities. And then the validation step is run it and see if it did exactly those activities. When you get a fine enough granularity, you can detect minute changes. Like it did n+1 operations instead of n. Why did it do that? And if I scale that up, is it going to turn into n squared instead of n+1 or what? So one thing that's key to this approach is you really want to avoid explaining your observations. And instead, you want to look at, I did this design, and therefore it should have this characteristic, and measure the difference. So this is kind of related to the concept of confirmation bias. But a lot of performance engineers suffer from kind of explaining why they get the results that they got, instead of trying to predict that and then seeing the difference and then analyzing what the difference is. So if I'm just explaining something, you can give me a pattern and I can say, oh yeah, that was formed by X, Y, and Z. Am I right? Probably not. I mean, there's 1,000 ways I could explain any particular pattern. But if I use a prediction and then validate my prediction, if my prediction's not based on strictly my observations, I'm going to have a lot more, my validation of that prediction is going to be a lot more high confidence. So that also is related to minimizing the number of parameters that we're trying to fit here, right? So instead of giving you 50,000 different parameters that if you set these just right, then your model fits exactly, if I can get that down to a handful of different parameters that I have to learn from the execution of the system, I'm going to have a much more accurate model. That's going to reduce my risk when extrapolating to large scales and large time periods. You guys are all going to do this at home tonight, right? Wait till you get to the next couple of parts here. OK, so just like with all these other ones, basically, once you've run this, you refine your model and you iterate again, right? So your refinement of the model might include things like fixing bugs that were in your code, but it might also involve making your model more accurately predict what you expect from your design to be what the code is doing. So iterating on this is also important, but micro-benchmarking and simulator, we can iterate very quickly. Predictive model validation, you're going to be running slightly scaled up tests, so it's harder to do quick iterations of this. And that's kind of why all the techniques come together. OK, so an example that we're going to use for predictive model validation is I've got a query system inside of Sqrrl. And what we do inside of that query system is we perform a lot of index intersections inside of iterators in Accumulo. So I'm not going to go deep into iterators, but suffice it to say that essentially what we're looking at is our iterators are going to seek through data. They're going to scan through data. So an iterator has a next call. It's got a seek call. And basically what I want to know is how many times am I calling next or seek to answer a particular query. So my query is fixed. My iterators do something. I ought to be able to predict how many times they're going to call on a given data set next and seek to find the result that they need. So this is where we get into spreadsheets for big data. Yay. You weren't expecting that, were you? So, boiling a big data system down into a consumable set of statistics also makes it so you can use all sorts of neat tools like spreadsheets for that. This is probably like version 7 of the model that we did for this particular query. This was a graph query that we did. It was looking at iterating through a neighborhood and selecting a particular subset of edges. So I've got an iterator stack, and I don't know if you guys can even read that, but at the bottom of this iterator stack is system iterators. So system iterators are those things that say, all right, I've got data in this tablet. Just give me back the key value pairs in this range. And on top of that, we do things like transform it. So interpret a key value pair. Say this key value pair actually means that this particular value is seen in this field of this document, right? And we build up, we basically compose this stack of iterators on top of those system iterators to form our information retrieval system. So each of these things has a slightly different function. And if I get very specific about what these do, I can say, every time I call next on this particular iterator, it's going to call next on its child iterator, or it's going to call seek. Or when I call seek, it's going to call next or seek. So this particular model just basically accounts for those calls to next and seek and tries to compose all of the things together. So with that, we can say, all right, if I'm going to look at 13 million edges, and I've got maybe, I don't know, something like a 10 billion edge graph that I'm running on, these are the number of operations that are going to happen in each of my iterators. And then, once we have a total number of nexts and seeks, we can assign a time to that, which is maybe through our micro benchmarking, we can figure out how long it actually takes to do next or a seek in the system iterators. And from that, we can account for the overall time that we spent doing all of these operations. So we did this. We did this on a fairly large customer's cluster, and found that we were actually doing like 10 billion nexts and seeks. And we looked at this query and said, should we be doing 10 billion nexts and seeks to return 13 million edges? Can we do better? And this is where you start to get insight into how to really optimize your code. So we said, for all these seeks that we're doing, maybe we don't need to do all the next calls. Maybe we just seek instead of doing that. Or instead of doing these seeks, maybe we can seek a little bit further and maybe push down a filter. So you get insights like that. Some iterators are going to seek or scan more than optimal. Changing the logic of the iterators or changing the order of those iterators can make a very significant difference in that. So as with all of the other methods, we improve the code. We revalidate, we change our prediction, and then see if the code execution actually reflects that. And through maybe 5 more cycles, we get a new spreadsheet. And you might notice that in this spreadsheet, I'm sure you guys all saw this already, there's a new iterator in there. You guys didn't see that? Oh. All right, so this iterator, the effect of adding a new iterator is not actually to do more work, it's to do significantly less work in this case. So instead of doing 10 billion nexts and seeks at the base there, now we're down to like 400 million nexts and seeks, which effectively, when you account for everything, we're 25x improvement on that. Right, so this type of overall predictive model really allows us to see what's going on, get a good idea for what we might be able to do better, understand whether, when we extrapolate to larger sets of data or larger clusters, whether our predicted performance calculations are going to scale or not. And the more accurate that you can get with this, like we got probably 3 orders of magnitude down when we were accounting for the different next and seek operations here, and got a very close match to the predictive model, close enough that we had a lot of confidence in what the system was doing. The more accurate that you can get, the less risk there is in extrapolating when you're talking about scaled up performance. So takeaways, performance is not good until you prove it. So these techniques, the micro-benchmarking, the simulation, the predictive modeling, is really all about proving that your performance is as good as you think it should be and you think it is. So don't expect performance to be good the first time you measure it. I've been doing optimized database design and coding for many years, and I never get it right the first time. I always learn something when I go measure. So make sure you do that with your applications. And then if you guys are interested in doing this type of modeling and simulation, let me know. I'd be happy to point you at some simple code that can do it, some libraries, or even help you out with design of that for your application. All right, anybody still awake? Anybody? Questions? So right now, these simulators are Sqrrls, but they're not core IP, so I'd be happy to share some stuff. I actually have a couple that I could probably share here. The compaction ratios for major compaction. Minor compaction, there's some other things that can affect that, like a merging minor compaction where you're... we don't use minor compactions because we do bulk ingest for the most part. I mean, we do metadata through streaming ingest, but yeah. So I haven't simulated that a whole lot, at least not in the last several years. Another question in the back? Keith, you mean like run the full system and see if it matches? So validating the simulator? So one thing that we have there is we have logs. So Accumulo, in its debug log, writes every time it does a compaction. So you can actually take those debug logs and you can reform the tree of compactions that happen. And we look at those and we see things like, oh, in the original version of the simulator, we didn't have complexity to look at contention between different compactions and whether they were falling behind. And that actually had a pretty big effect on average number of files that showed up. So comparing the simulator with the actual trace of compactions, yeah, it does give you good insights. We actually don't do it that frequently. We should probably do it more frequently, but there's only so much that you can do. Yeah, it would be nice to have those types of stats available, long-term captured by Accumulo. Just sort of in the metrics and monitoring of the system. Oh, right. So we actually put another iterator in place that basically accounted for those calls. It just had a counter and a mechanism for retrieving that counter and logging it occasionally. Not every microsecond or not every operation, which would be 100 nanoseconds. But when it got to 1,000, it would sort of output something. So yeah, at the end of the query, we basically, from a top-level iterator, called the stats on this lower-level iterator and aggregated it appropriately. I don't know if there's stuff in the Accumulo code base. We've been doing this for years, so I think we actually used something that is in the Accumulo code base to do that, like an accounting iterator. I can't remember the exact name of it. Maybe accounting. Yeah. Cool. Anybody else? Anybody else? You guys save me any cookies? This talk was really about cookies. All right, thanks.